okay. David, you've got your hand up. Can't hear you.
I think that was
It's an applause. It's an applause.
Oh, an applause. Oh, sorry. Oh, applause. Yes, absolutely. Sorry.
All right. Thanks. Congratulations, Sid, and thank you, Don and Laurie. All right, let's move along to our feature speaker today. This gentleman hardly needs an introduction. He's a board member on the Friends of the DAO and has been an active participant here for quite a while. And oh yeah, he hosts.
Sorry, Aaron.
You might have heard of it. Oh yeah, Quirks and Quarks.
Sorry,
Aaron, hold on a minute, please.
Aaron, sorry.
Yeah.
There are people on YouTube that can't get in. So if you could just, can we just hold for a quick moment? I'm just going to switch them to Zoom, I think is probably.
Okay, yes. In the meantime, I can answer a question we got in chat. Yeah, so we've got a question from Haley. How do you get an asteroid named after you? And you have to have someone who's really good at finding asteroids name it after you. Basically, the person who discovers an asteroid and characterizes its orbit is the person who gets to name it. And there's a gentleman, an astronomer here at the DAO, who is just phenomenal at finding asteroids. David Balaam is his name, and he has found, I think, over 2,000 asteroids and other rocks up in the sky. So he has named several after a whole bunch of different local figures. I believe, Bob, you have one named after you. Is that correct?
Yes, I do. Yes,
yep.
I do.
There's one named after, was it Picachin, I think? One of the local First Nations communities here. Sid's got one named after him. Several other people in Victoria. I think we probably have the highest per capita frequency of people having an asteroid named after them. Due primarily to Dave. Okay.
Aaron, I was just going to say that I think it was Eleanor Helen down in, I'm not sure I'm pronouncing her name right, but she found this asteroid back in the 90s. So it was quite a long time before it got named.
Oh, wow.
In this case. Yeah. So I think somebody else actually submitted the name. Maybe Laurie or Sid, maybe you can mention if you remember who suggested the name in this case.
Yeah, Chris first submitted my name, and actually this asteroid was discovered in 1992 at Palomar Observatory.
Oh,
So
wow.
yeah, so it's the IAU who gave, I think after the nomination, they offered to nominate some not so worthy people. So I'm one of them.
Well,
not true.
No, with all of your work you've done, you definitely deserve it. Okay, so I think we've got the folks from YouTube over here now. So without further ado, let's turn things over to Bob McDonald, who's going to be telling us about the productive intersection of art and science.
Well, thank you very much, Aaron, and thank you everyone for joining us tonight. It's a real pleasure. I want to share with you some of my personal art that I have here. Also, there are some people who are on Zoom or something who have their microphones open, and when you talk in the room, it's coming through. So if you want to mute your mics and talk to us through the chat, that makes it easier, because otherwise I'm hearing funny voices when I'm talking, and I have enough funny voices in my head as it goes, like Marlene in Victoria, for example. So yes, art and science. Whenever art and science get together, it's usually a beautiful thing. And yeah, who's Marlene? She's doing the dishes or something. It's really annoying. It's usually a beautiful thing when art and science come together, and very often they need each other. The science very often is only visible in data. And then the artist will come along and bring it to life. Like, we don't really know what black holes look like, but artists can show us, give us an idea, give us an impression. And artists can also take abstract ideas and, well, turn science into poetry in a way. And I'm going to show you some examples of that as well. And the first bit of art that I want to show you is the one that's right here over my shoulder. This is a painting that appeared in the original television series Cosmos, hosted by late Carl Sagan. And it was painted by astronomical artist John Lomberg. And it's a picture of our Milky Way as it would appear from about 10,000 light years up above the plane, looking over the top. And this was used in the series when they were doing a cosmic zoom from the Milky Way down to the Earth. And what's interesting about this is that this is a photograph. If it ever turns into a photograph, we will never get this photograph. I mean, that is the equivalent of the Earthrise picture that they took from the Apollo missions of the moon, with the Earth rising above the lunar surface. The first time that humanity saw itself as one single unit. Well, this is the next step of that, when we can step away and see our galaxy as one single unit. Well, of course we can't, because we're in it. And it's too damn big to get away from it far enough to see it. It took 3 days to get to the moon to see the Earth. And by the way, they don't see the whole Earth on the International Space Station today. They're only 400 kilometers up. They see the curve, but they can't see the whole thing. So it was only the humans who went to the moon who saw the whole Earth. To get this view, like I say, you'd have to go up 10,000 light years. So that means, well, even the Starship Enterprise traveling at warp 10 would still take 1,000 years to get up there. So unless we develop some ultra fast spaceships, or if aliens, maybe up in the Magellanic Clouds who can see us from up there, come down and give us this picture, we'll never get it. So it's the artist. It's the artist who tried to interpret what our Milky Way looks like. And I'm going to come back to this in a little bit. I'm a big fan of John Lomberg's art because, well, I think he's a great artist, but also because I know him personally. John and I shared a house in Toronto in the 1970s. So John and I lived together with a few other people back in our alternate lifestyle days. We're a couple of latent hippies. And I was with John when he met Carl Sagan, when he was involved in the Voyager project, and when he was involved in Cosmos. So John introduced me to Sagan, he introduced me to Voyager, and he introduced me to CBC Radio. So if it wasn't for John, I probably wouldn't even be where I am right now. And one of the other paintings that I have of his that he did, again, this is back in the 1970s, he did this. I think he did this in about 73 or 1974. This is gonna be awkward because I'm just gonna try to show you things here on my camera. Now remember, this is before Hubble. This is, if you can see this, if I can show you this. This is the galaxy Centaurus A. And look at the detail that he put into the center. I got some reflections here that are coming off the glass. Those are Venetian blinds. It's not in the picture. Look at the detail that he put into that with the dust lanes. And you really have to see this in person, because it's very spherical. It's a beautiful, the way the light shines on it. It's very, very spherical. A trillion stars with an incredible amount of energy on the inside, and those amazing dust lanes that we now have close-up pictures of, thanks to the Hubble telescope. But John did that problem. Another one that he did, John likes to do metaphorical art, where he'll take concepts, ideas, and put them into a space context. And this is one that was on the webpage earlier here. And this is the, I don't know if I can get this one. Here we are. It's such a big painting, I can't get it in the frame. But this is the Earth on the back of the sea turtle. Both I think the Babylonians and the Hindu had the idea of the Earth flying through space on the back of a big turtle. John made it a spherical Earth, not a flat Earth, because the flat earthers now today like to use this idea that we're a disc and not a ball. And also right in the center, right here, is the islands of Hawaii, because that's where John lives now. on the island of Hawaii. So he's got it in the center of the photograph. But yeah, there was a belief for a while that we didn't know what held the Earth up. Why not give it to the great creatures? That the Earth would be on the back of a giant turtle or elephant or something like that. And I just want to show you one more. Again, this one's very large. It's kind of hard to show you. This is based on a short story that John heard called Your Move Black. And the story is about a space traveler who is, God, I just can't get here. Hang on. I should have practiced this ahead of time. Didn't realize how big these are. Can you get the sense of what that is there? I know it's hard to see. It's the Horsehead Nebula. So the story is that a space traveler was out visiting the Horsehead Nebula, and all of a sudden this giant hand comes down and replaces it with a luminous bishop, as though the Horsehead Nebula is a knight. And it's called Your Turn Black. So this is a metaphor for stars coming out of nebulae and nebulae giving birth to stars, the continuous recycling of stars. I hope you can see that. It's kind of an awkward thing to show you like this. I've never shown paintings on television before. But that's some of the work that John Lomberg has done, and I suggest you go to his webpage to see it. So let me introduce you to John. He's got some interesting stories to tell. Bear with me here for one moment. And let me see if I can make this work. There he is. So this is John. This is how I met him. I met him when he was inside one of his paintings. I worked at the Ontario Science Centre in Toronto in the 1970s, and John was brought in to paint an exhibit. And it's a three-dimensional galaxy. It's a three-dimensional model of our Milky Way. And the way he did it was to have, I think it's about 8 layers of plexiglass. And he painted three-dimensionally on all of those layers so that, and he used fluorescent paint with black lights above and below so that the galaxy is suspended in the middle of space. It's suspended, and it's beautiful. It's still on display at the Science Center today. The problem is, if you really want to see it, you need to be in a totally dark room. And they told me there's this artist downstairs in a room that he had taken over and completely blacked out. You should go down and see him. So I go down, and here's this guy, and he's within his own galaxy. And so we sat and we talked, and you could actually go below the plane and look up at it, or you could go above the plane and look down at it, and you could go around this way three-dimensionally. It's an absolutely beautiful thing. The problem was when we tried to put it on display for the public, the lights in the room would reflect off the plexi and it would take it away. So they had to actually encase it so that you look through little portholes. But I believe it's still at the Science Center today. So that's how I met John Lomberg. John told me about how he met Carl Sagan, because here's this painting being used in the Cosmos series with Carl looking out over his spaceship of the imagination. And I said, how did you guys meet? Because John also illustrated Carl's books, and then he became chief artist here. And John said, well, I heard about Sagan and I wanted him to see my art. Now, this is before the internet. This is in the 1970s. It's before web pages. It's before home computers. So John wrote a letter to Carl Sagan at Cornell University. Remember when we used to write on paper and put them in little envelopes and stick them in a box, and a nice man would come along and take it away to wherever you wanted? Anyway, he wrote a letter, and Sagan wrote him back and said, I'm coming to Toronto for some business. I'll meet you at the airport. I'll give you a few minutes at the airport. That's all I have. So John thought, okay. So he went to the airport to go meet him, but then he thought, I don't know what Carl Sagan looks like. Because again, he couldn't go to a webpage and get a picture of it. And Sagan didn't know what John looked like. So he said, well, how are we going to meet? So what he did, he took a long strip of paper and he wrote out the Drake formula. The Drake formula that Frank Drake came up with to calculate the number of intelligent civilizations in the galaxy. And John thought there's only one person on this flight who would know what this is. Nobody else will recognize it. And he taped it to the side of his portfolio that had all his paintings in it, and he just held it up over his head. And when the flight got off, this guy got off the plane, looked at him, and walked right over and said, "Hi, I'm Carl Sagan." So that's how they met. And it was an interesting exercise in communicating with someone you don't know. And John was saying that that's the kind of thing that we need if we're going to communicate with other civilizations. We need to find some kind of common language that both of us would understand so that we communicate. And so far, the best of that's been mathematics, I guess. But it was just sort of a funny story of how they met. This is a better galaxy that John painted because he was told that this one is too bright. The stars wouldn't really look like that. So he did do another one. And this one hung in the Air and Space Museum in Washington for about 10 years. They now have it in their archive. And the Earth is right in the very center of the frame. It's right in the center of the frame. So it's the artist. It's the artist who will give us the perspective on our own galaxy that we only know otherwise by data from radio telescopes and what it looks like and other means. Here's John and I at the Voyager, I believe this is Voyager Neptune in 1986. Both of us had sort of cleaned up our act quite a bit. I was hosting a kid show called Wonderstruck. But we're standing at the Jet Propulsion Laboratory in front of the model of Voyager, or the backup, the test model that they use on Earth. And you can see the golden record there just off John's shoulder. And this, of course, is the message that Carl Sagan convinced NASA to put on the side of Voyager. And John did the drawing that's on the outside, which are the instructions on how to play it. At the upper left, that circle, that's showing that this is a record, because again, 1970s, CDs hadn't been invented yet, even though digitization was invented. So this is a digital record. And so the circle shows that this is a thing that you put a needle on, and they gave them the needle. There's a needle in there with it to play it. They give them the frequency of the first sound that they're going to hear. There's a star map at the lower left there that shows where we are compared to 14 pulsars. And the two squares that are in center there, that's the first picture that you get when you play this thing. It turns into a circle, and that's just a calibration circle. So anyway, John designed that. And that's now art that's going to last for 1 billion years. It's pretty amazing to think about that. And I joined John and Carl Sagan and Frank Drake and the whole team that put the Voyager record together to go down to Cape Canaveral and watch Voyager launch. And it was an amazing experience for me to be with this group that had put together a message to anyone out there. We watched this thing disappear that humanity will never see again. Sagan was in tears when it took off because he just kind of looked at the rest of us and he said, we just sent a spaceship to the stars. We just sent a spaceship to the stars, because we've only, now that New Horizons is out there, we've only had five objects that have ever left our solar system. And we got really, really quiet on the way back in the van, because everybody was thinking about this thing that we had just sent from Earth out to the galaxy, and we'll die. Humanity could probably die, will probably die off. The continents are going to move, ice ages will come and go, the Earth is going to change, new species will come here, and that thing will still be out there. And it was a very profound thing. So we sent art. John also did some of the drawings inside. We did some of the drawings inside as well. Plus there's music, and there's pictures. There's 117 pictures. So we sent art to the stars. I think that's really cool that we want whoever finds it, if it ever is found, to know a little bit about us, a little bit about our spirit, not just our technology. So that's my story with John Lomberg. His latest project in Hawaii, which you can visit, is called the Galaxy Garden. And it's a 100-foot wide model of the Milky Way, built as accurately as possible. And you can walk through it and try to find the sun. And the plants that are in it represent various nebulae and whatever. And there's, if you do find it, it's one speck on one leaf of one plant. And 1 inch is 83 light years. So it's kind of neat that you can go in and walk through the galaxy. And then if you make it all the way to the center, there's a fountain there in the shape of a gravity well. That represents the black hole in the middle of the garden. So if you're ever in Hawaii and you go to the Big Island, not far from Kona is where the Galaxy Garden is. And John doesn't live far from there. You might even have a chance to meet him as well. He's quite a guy. Anyway, so how about some other artists? Well, astronomy began with art out of necessity. Galileo had to draw what he saw because photography hadn't been invented yet. And when he looked at the moons of Jupiter, which is what this is, looking at it night after night, noticing that those moons were shifting position from side to side, the Galilean satellites, which we can now watch with our small telescopes. And you can, in fact, I was doing it not too long ago. It was his drawings that presented empirical evidence that little things go around big things. So our little planet probably goes around our big star, big sun. And even though that wasn't his original idea, it was Copernicus that had the sun-centric idea, but Galileo came up with empirical evidence that you could really measure. And he was so anxious to tell the Pope. Anyway, so astronomy began with art. Astronomers had to draw what they see. And when Galileo looked at Saturn, he thought it had ears, Mickey Mouse ears. Well, I guess Mickey Mouse didn't exist then, but it had handles or something on the side. Didn't quite know what was going on there. And then as he kept watching it, of course, the Saturn went around, the rings went edge on, and they disappeared. And Galileo said, "My glass has deceived me," because what he had seen before was gone. Now we know that Saturn's rings are indeed like that. Then we had Percival Lowell. And if you have not had a chance to visit the Lowell Museum in Flagstaff, Arizona, go there. This telescope is still used. They still do astronomy with it. And they give great tours. They have a wonderful visitor center there. They also have the telescope that Clyde Tombaugh used to discover Pluto, and lots of exhibits on that. So I really recommend it. But again, Lowell had to draw what he saw, and he was a little biased. He looked at Mars, he was obsessed with Mars, and he believed that he saw lines on Mars. Now, there was an astronomer before him, Schiaparelli, who saw lines on Mars. Schiaparelli called them canali, which means channel. Channels are natural. Lowell called them canals, which are artificial. And this is a case where if you want to see something, you'll see it. And so this was his belief, which is kind of backwards to the way astronomy should work. You shouldn't have a preconceived idea of what you're going to find. You should be open-minded, but he was determined that there were canals on Mars. And if there are canals, that means that there must be Martians there building them. And if these canals can crisscross an entire planet like that, then the Martians are incredible engineers. Because the biggest canals that we have on Earth, the Suez Canal, the Panama Canal, they're puny compared to this. So those Martians are incredible engineers. And of course, if they're engineers, maybe they could build spaceships, maybe they could come here, maybe they could do terrible things to us, who knows? And so that, of course, got the War of the Worlds and all these other ideas off. Here's a fun cover of a magazine that was done based on what was known about Mars at the time. And I think this thing's really fabulous. If you look at well, first of all, the Martian is a lot taller than the human because the gravity of Mars is lighter. It's only 1/3 of what our gravity is, so they can grow taller there. The feet are big pads for getting around on the sand dunes because they knew that Mars was probably a desert. That's why it had canals. It had to irrigate water from the poles down to where the cities are. The legs are kind of skinny, at least at the bottom, because again, the gravity's low. You don't need gigantic muscles. The chest is huge because the Martian atmosphere is so thin that you would have to take in huge amounts of air to breathe. The ears are really large for the same reason. Sound does not carry very well in thin air, so they need big ears. The eyes are large because Mars is farther from the sun. It's a little bit dimmer there, not quite as bright. The long nose, I'm not quite sure about. maybe that's for digging into the sand or something. And then there are antennas sticking out of the forehead because, well, all Martians have antennas sticking out of their forehead. I don't know what they're supposed to do, but at least it was, based on knowledge of the time. So you could say that for what they knew, this is as good a guess as any, as scientifically accurate, an artist's representation of what life on Mars might look like. Of course, we humans are a little more violent than that. So H.G. Wells does The War of the Worlds, then we get the movie, and we get Orson Welles with his famous Halloween radio broadcast, and artists on comic books describing their horrible machines that would take over the Earth. I was wondering today, I wonder if the virus that ultimately killed off the Martians in the War of the Worlds, I wonder if that was a coronavirus. Maybe, maybe it was, or was it influenza? I think it was a common cold, I don't know. But a virus, boy, we're still fighting them, right? We're still fighting the bloody viruses, but the Martians could not beat our virus. These comic book covers are really quite amazing. I'm gonna have more of these in just a second. But art, bringing science to the public, bringing science imagination to the public, firing the imaginations of young people. It was the artists who did that. We did, in fact, find channels on Mars. So Schiaparelli was right, but unfortunately, Percival Lowell was not. We haven't seen any canals yet. We haven't seen any cities, although Richard Hoagland does believe that there are pyramids there and the face on Mars and whatnot, but I don't subscribe to that particular thing. So Mars does indeed have channels, but there's no water in them today. But that's what Curiosity rover is doing, is looking along these river valleys and dried up lake beds to see how Mars was in the past when it was wet at one time. One of my favorite artists when I was a kid was Chessie Bonestell. Bonestell was incredibly accurate. He was a realistic artist, and he worked with Wernher von Braun to come up with scenarios for space. And this is his version of a future space station and a winged space shuttle, which we ultimately did build. It didn't quite look like that, but it was a winged space shuttle. The space station, we didn't build it round yet for artificial gravity, although they did pick up that idea, Stanley Kubrick did, in the movie 2001: A Space Odyssey. And the reason they want it round is that you would stick to the walls and have artificial gravity on the inside. I may have shown this, I think I showed this picture myself. I commissioned an artist to draw my version of what a swimming pool in a space station like that would look like. If it was built on the outer rim, it would just be a regular pool. It would have a curve to it, but it would be a regular pool. But I would like to see a pool in the middle, right in the center hub, and so that it would look sort of like this. And it would rotate so that the water would stick to the walls, so you'd be able to swim all the way around. And with the ladders, you could climb up to that central hub where you'd be weightless, so you could dive in any direction. I commissioned David Sheridan, an artist in Ontario, to do this for me, and he brought it to life. I had to spend some time with him describing it to him, and the way he did it, he went to his daughter's swimming lesson. That's his daughter in the lower left there. He just went to the swimming lesson. They went to the edge of the pool, and he just sat there and he said, okay, what would this pool look like if it wrapped all the way up around into the ceiling? And this is what he came up with. And I really admire his work to take my concept of a cylindrical swimming pool and put it into space. By the way, the lifeguards are in the middle there. That's you could dive in any direction you like. It'd be kind of neat. We've got to do this. We got to build one of these. Chessie Bonestell also showed rockets that, of course, they looked a lot like the V2 rocket, which was the most popular rocket at the time. And but I found this one that he did, and I thought it was very similar to one that we have today. I wonder if Elon Musk and his Starship took inspiration from Chessie Bonestell. Boy, they sure look alike, don't they? Here they are. Look at that. And then, of course, Bonestell did these wonderful landscapes of what it would be like to be on moons of the different planets. And this is looking at Saturn from Mimas. This is a painting that was done in 1958. 1958. And What's interesting about the moon itself, you can see the cliffs are very, very sharp. And we've been finding that, at least on our moon, you don't get those jagged cliffs. Everything's been kind of rounded out because of pulverization from micrometeoroids hitting them all the time. But what Bonestell showed in this picture is that if you're there at Saturn and not from our perspective on Earth, where the light is always behind us, we always see Saturn fully lit, that if you were there, the rings indeed would be very thin and they would cast a shadow on the planet. So you would see that dark band on the surface of Saturn. Well, here's an actual photograph taken from Cassini. And look at how similar it is to the Bonestell painting. That's looking over Titan, not Mimas. But look, the rings are really thin and there's that shadow on the surface. So Bonestell brought that to life in 1958. I find that astounding that the artist was able to imagine what astronomers had told him that Saturn would look like if you were there. That's the beauty of art. Of course, other artists without Bonestell's high resolution had fun with it, with these things. Here we are skating. I don't know if we're still on Mimas or not, but being able to skate. And miraculously, the moon has air, so everybody's having a good time. I don't know why those ships are up on top of the mountains. I have no idea what that is. But again, everybody likes to go to Saturn. We always draw Saturn. Women represented in classical science fiction art did not do well. They were either damsels who needed to be rescued by really hunky white guys, and they were usually not wearing very much apparel. They were either being rescued or they were being tortured or worked on. So they were victims, but not always. Even if they were put in a position of power, and they were, the women were the captains of ships, their spacesuits were still quite skimpy. I mean, look at the difference between her spacesuit and his spacesuit. His is nice and bulky and loose fitting, and hers is, well, yeah, it's a little different, a little different. And even bare skin works in empty space. So boy, those women are tough. But women in art out of the 1950s, you can tell that these paintings were all done by guys, probably young guys. Even when the women were torturing the men, they still didn't wear much. So this is, I think today's art is representing women a little differently. So it was terribly, terribly chauvinistic, where art got this, took a little too much license, I guess. We still have today science asking art to represent what we see with our robots. Now, even though we're going to the planets. So this is an ice cliff on a moon of Uranus called Miranda. And Miranda is a very tiny moon. It's only a few hundred kilometers across. You'd hardly weigh anything there. It's so small, the gravity would be incredibly low. And this cliff, which is that triangular shape in the middle of the picture, you have to kind of get your head into it. The upper right is a flat plane. The triangle is a sheer cliff face of ice. And then the bottom of the cliff is down towards the lower left. That wall is 10 to 12 kilometers high. 10 to 12 kilometers high. You can have big cliffs like that on these little tiny moons because the gravity is so low that the gravity won't pull it down. And I just try to imagine what that would look like to see a wall of ice 10 kilometers high. But an artist took the liberty to say, well, you could take a flying leap off that. If a kid took a jump, it would take about 10 minutes to make it to the bottom. And they would just float down like a leaf. You come down really, really slowly, sort of like the lander that tried to land on, the Rosetta lander that tried to land on the comet, came down so slow that it just sort of bounced off the surface. So you could literally take a flying leap on this little moon of Uranus. And Uranus would be up there in the sky at the top. It'd be quite beautiful with its dark rings. Of course, we try to represent things like gravity. Gravity, well, Einstein's idea of curved space. Although this one, I'm kind of disappointed in this one. It does show the gravity well of both the sun and the earth, but they got the scale all wrong. I mean, the earth is way too big and way too close to the sun. However, it's It's an attempt. It's an attempt to show the invisible force of gravity as Einstein would see it, at least in 2 dimensions, your classic gravity well. And then, of course, we had computer art try to show us what black holes would look like. This image was very popular during the time that the gravitational waves were detected by the LIGO instrument, showing the collision of 2 black holes and how they would distort space. Excuse me. And just before that, we had the black hole represented in the movie Interstellar, which was a horrible movie in my mind. That's just my opinion. But this image of the black hole is considered one of the most accurate. And Kip Thorne, who went on to win the Nobel Prize in physics, who studies black holes and who's a specialist in it, he worked with the movie producers to come up with this image. And it shows the accretion disk and the light being distorted as it goes around the black hole so that the disk seems to come up on the backside. So again, artists representing what science can only see in data. And it's really valuable to bring that to the public, to get the public interested in black holes. I don't think the public would be as interested in black holes if we didn't have these kinds of representations of them in movies and in magazines. Just in other subjects besides space, I find this graphic. The US Geological Survey wanted to show how much water the Earth has. And so they did this little graphic. And if you took all the water on Earth and put it into one drop, that's how big it would be. The big one is salt water, and the little one is fresh water. So that's it. That's how much water the Earth has. It's not much. It's not much. And 7 billion people have to drink that little drop. And it's one of the big issues of the 21st century is water. But I thought that was a very, very dramatic way to do that, to represent it graphically like this. And in biology, medical art is really important for teaching medicine. A friend of mine that I went to high school with, he thought he wanted to be a doctor, and he went to medical school for first year. And he said, you look at these diagrams in books, and all the organs are nice different colors, and they're all separated so that you can see them and you learn what they're all about and how they work. He said, then he went to the first anatomy class where they had a cadaver. And he said, first of all, they open up the body, and about 3 people fall to the floor, fainting. But he said, when you look down, all you see are guts. Everything is red. You can't tell the heart from the lungs, from the intestines, from the liver, or anything. And he said, that's one of the biggest challenges in surgery, is actually finding the organ that you're looking at, because you're just putting your hands in all this red gut stuff. He said, it's not like the textbooks. So it's the art in the textbooks that has to tell them, here's what a lung looks like, here's what it's shaped like. And so it's medical art. Medical art is really important for teaching. And I just want to leave you with this picture of myself. This is in 2015, I went to Baltimore to watch New Horizons pass by Pluto. And I have a model of New Horizons in my hand. New Horizons is a bit bigger than that. It's about the size of a piano. And in my hand is this book that I got when I was 7 years old. My mother came home with this book, and it's simply called The Planets. It's a Golden Library of Knowledge. And it's an art book, because in 1958, the year after Sputnik went up, we didn't know what the planets looked like. We hadn't been there. We just knew them in telescopes. And this book just has images of what the planets might look like. It's very realistic. I was just reading this as an actual book. It could still work as a kid's textbook today. It's very scientifically accurate. And that inspired me to get interested in science, in space, was an artist. And it turns out it's actually a Russian artist did this book. So I thought it was poetic for me, profound, to have learned about Pluto. And in this book, it's nothing but a dot. To learn about Pluto when I was 7 years old and actually be there when we went to Pluto. And it's actually been supremely enjoyable for me to be witness to the exploration of this very solar system as a working journalist, to be there at the Jet Propulsion Lab or at Johns Hopkins University and watch images come in from these worlds and see them for the very first time. It's just been a tremendous, tremendous joy. And I want to leave you with one last little thing, just a short video. And I'll stop sharing my screen here. Whenever we send robots out to these planets, you always get computer animation from NASA that shows the perspective of the spacecraft. So let's run this video, and they look very nice. It shows the public how they're going to work, but what they're really doing. I visited the computer lab at JPL where they make these videos, and they make them way ahead of the mission, and they're actually useful for the scientists. Oop, have we got it running here? Oh, there it is. Okay. See if it'll run. Here we go. Okay, we're on our way by Saturn. This is Voyager passing Saturn. Those are actual pictures of Saturn that Voyager took on the way in once it got there. But the scientists use these animations to show the three-dimensional perspective of where the spacecraft is going to be at every second during the flight. And also where all the objects are going to be, where Saturn's going to be, where the rings are, when they cross the ring plane like that, where the moons are going to be, and what the perspective is so that they know where to point the cameras. And it's these animations that will say, oh, at timeline such and such and such, Titan is going to be off to our left. One of the other moons is going to be over here. The rings are going to be down here. We're going to see the shadow of the planet. And they plan the mission. Especially for the flyby missions, because in a flyby mission, you're only going by once. It's like you go on a tour and you can't get out of the bus. You got to take all your pictures out the window. So they have to know where everything is before they get there, and they use these animations. So art helps the science. Art gives the science the perspectives even before they go there, so that they know. So in my mind, we need art. We need art for the realism of it. To bring science to life, to help science display itself to the public, to help the scientists themselves understand it. But we also need the imagination of artists. We need the poetry. We need the fantasy. And it's part of our human spirit. And I think that scientific art really, really brings that alive. So that's my presentation for tonight. I hope you enjoyed it. And thank you all very much for joining me tonight. Thank you.
Thanks so much, Bob. Fantastic to see those paintings and some of the development of of art and science informing each other through the last century or so. I definitely wouldn't want to be stuck in one of those spacesuits from the comic book covers. Let's see. Do we have any questions? If you do have any questions for Ben, or Bob, please toss them into the chat either on Zoom or YouTube. Sorry, I just found a question from Ben. Ben asks Lori asks what the disc is made of on Voyager. Oh, it's gold. It's a gold record, literally, because gold will withstand the bombardment of the micrometeorite that it might run into. Intergalactic dust is pretty thin, but no, it's literally a gold record and a gold cover as well. Yeah. Is that just because gold is more malleable? It's not going to like shatter. It'll hold itself together for 1 billion years. Yeah. Wow. Yeah. Any other alloy could deteriorate or corrode or whatever, but gold will hold its own. Oh, that's really interesting. Gold doesn't rust. Yeah.
I had one other question, Aaron.
Yeah, go ahead, Lori.
If I could. Bob, one time last summer, some of the students who were at UVic were showing how they could do a lot of art on their iPads. Like they were actually doing all of the like beautiful coloring, and it was like coloring, but on an iPad. Have you seen a lot of that or know of people who are doing that kind of work?
Well, actually, one of the people who is doing that is John Lomberg. he now works with computer art. John, what happened to your paintbrush? Come on, you do those little splatters with your paintbrush to make the stars. And well, now I can do it on the computer. So he's one. I think we're seeing more and more of it. I think it has its place, but art that's done by hand has another feel to it. It's like people argue the difference between film and video. Like they don't look the same. There's a difference. And I think we still need the hand. We still need the hand. But I'm all for computer art. Go for it. But I don't have any talent at all drawing. I can do stick figures. That's about it. So if I'm going to do any art, I'll need a computer. So I think we need both. We need both.
I agree. Let's see. Janine asks if you've seen the art displayed at Triumph. There were some artists commissioned to create some works based on the work they do there. I'll see if I can bring it up here.
It's been so long since I've been to Triumph, I can't remember what's on the wall.
Yeah. There's a couple of different ones here. I'm trying to find one of them. The website is not super navigable for this. Might have to come back to it.
Okay. Well, thank you everyone for your questions, and thanks for having me tonight.
Yes, thank you. Thank you so much, Bob. And if we have any more questions, if you're still around, we'll pass them along to you as well.
Sure.
All right. So next up, we've got Lori and I are going to share a bit of some recent space news. We've got stuff coming up and stuff coming down. Lori, which do you want to do first? Oh, you're muted.
You could go ahead and start with some of the stuff that's coming down.
All right. Yeah, so two little news stories. So one of them is some of the Starlink satellites that were sent up by SpaceX recently didn't quite make it. They got dragged back down to Earth by the sun, strangely enough. Shortly after launch, the Earth was hit by a geomagnetic storm. This is a puff of solar wind that swings by the Earth every now and then. And it plays with our magnetic field. We usually get some nice aurorae. But what can also happen is that it heats up the upper atmosphere, which literally puffs it up. So the upper atmosphere becomes thicker than it usually is and denser at higher altitudes. So these spacecraft had just been launched, and they were in a temporary, very low orbit just to make sure that all of their systems were working. SpaceX wants to make sure that those systems are fully operational before they boost them up to a higher orbit where they'll sit for a longer time. And that way, if stuff isn't working, they can deorbit that satellite and it'll burn up in the atmosphere. Unfortunately, rather than the satellites going to the atmosphere came to the satellites and took out about 2/3 of that group of close to 40 satellites that were recently launched. So that is unfortunately several million dollars of hardware. But luckily, because these are designed to burn up completely in the atmosphere, there's no risk to humans from that. So that's some stuff coming down. Or do you want to do a stuff coming up story, and then I'll swap back?
I was going to say we could sometime have a good philosophical and scientific discussion about whether or not the Starlink satellites should be up there. And maybe I did hear a couple of people say, oh dear, we lost some Starlink satellites. And there didn't seem to be, there were a few people that weren't all that terribly worried about that.
I'll just say that I was not terribly emotionally invested in the success of these satellites.
Yeah, we did a piece on that on Quirks and Quarks last week about how it's going official now with whether or not there should be laws and whether astronomers should know when the satellites are coming over for the big telescopes. So they've actually set up a commission now on it. So
Yeah, I think at the very least, like the orbits should be published so that astronomers can work around them, because they do get in the way of pictures on a lot of these telescopes and can cause some issues, even if you're not like, even if you like clear your camera, if the satellite was there, there's some persistence effects that can ruin future photos as well. So personally, I think they shouldn't be up there until we have telescopes on the moon. But that's just me.
Bob, who was the person that you had as your guest?
Oh, you had to ask me that, don't you? Go to the Quarks and Quarks webpage.
Hey, someone
I-
called Benvenuti, right?
Benvenuti, yes, that's correct in Italian. He's the head of it now.
Okay.
Yes.
But it's
Thank
on
you. I'm
last
sorry.
week's
Shows
show.
that
Just
I
go-
was actually listening.
Yeah, go to the webpage, Quarks and Quarks, and you'll see it.
Okay, I'm sorry to put you on such thing. So I've got another just a little bit of a sharing of my screen that I would like to do, that is talks a little bit about share sound, and yeah, okay. It shares a little bit about some of the space news that we've been talking about. And I know that at least I knew in the audience before that Chris Gaynor was online here just a little while ago, and maybe Chris can help me out here if I, or a lot of other people here that might know an awful lot more about this. But we've been focusing on James Webb ever since we were able to, as the FDAO was asked by the Canadian Space Agency to help out with some of the before the launch. So we had 4 of our HAA astronomers come and talk to us, and we're all still really interested in what's happening. And I know that some of you probably have seen this picture that came out just about now, I'm thinking maybe 10 days ago or so, that were the famous 18 dots. That is the first visual images that were taken by the James Webb, and in fact these dots are all the same star, but taken by the 18 different parts of the mirror segments, the hexagonal mirror segments that were taken by them, and this was kind of the first picture that they came up with of this star that's actually in, I believe, Ursa Major, a little bit just off of Ursa Major is one of the stars that they took. Well, then just the other day, maybe yesterday or the day before, they came out with that they had taken these images right here, and they had placed them so that exactly where they would be kind of in the 18 mirror segments, and which mirror segment was looking at which one. And then, so now what they will do is try to align so that now they will constantly kind of just move the segments around and focus these mirror segments so that eventually everything will be kind of in one focus that's there. Now I was able to get, and I'm hoping this will work, I don't guarantee this at all, that this is a little just about a 3-minute video or so that talks about exactly how they're going to do that way better than I can. So I'm hoping that this will work, and you can let me know if people can see this.
Well, first of all, the first evaluation images came in the middle of the night, but the team all came in, and we gathered and we evaluated whether the camera was working well enough for us to proceed on with the alignment. And as we analyzed those first, photons, if you will, the team was pretty positive that the camera was working properly and the instrument was working properly.
Sorry. Sorry. I'll put it on from that slide. Yeah. Okay. Sorry. Want me to start again? No. Oh, is it? Is it going again?
Well, first
Sorry.
of all, the first
Sorry, everybody.
evaluation images came in the middle of the night, but the team all came in and we gathered and we evaluated
Oh, what happened?
whether the camera was working well enough for us to proceed on with the alignment. And as we analyzed those first, photons, if you will, the team was pretty positive that the camera was working properly and the instrument was working properly. So we picked a star that was very bright and didn't have any stars near it that would contaminate the image. We know that the primary mirror segments aren't aligned, so they actually act like 18 separate telescopes, and we expect to see 18 separate images, one for each mirror, that are a little bit blurry at this point because we haven't aligned or focused anything. And so we pointed at a bright star and we made a mosaic. We actually took the near-infrared camera and we took images in different parts of the sky, and then we looked for the 18 spots from the 18 different telescopes, if you will. And we were very excited to find them. And the 18 spots were actually fairly close to each other. So really everything was very close to what was predicted. We've identified which of the 18 spots is which mirror. At this point, we even know which ones are from the wings. And it turns out one of the wings, you can actually see those 3 spots are a little farther over. And that's sort of what we expected. So we've identified all 18 spots, and the next step is to make an array of them. And then we're ready to start what we call global alignment, which is when each of those 18 spots will start to be aligned and focused. And that's sort of the last step before we take those 18 spots and put them on top of each other to start forming a single star going through the 18 separate telescopes. That's the work that will be starting soon. We also took a selfie of the primary mirror. We took an image of the primary mirror, and that helps us understand the alignment of the telescope, especially the primary mirror, to the camera itself and the instruments. There's actually a special lens in the near-infrared camera that you can put in, and it allows you to take a picture of the primary mirror itself. And in this particular case, one of the segments is pointing at a star, so that is the segment that lights up. But you can see the outline through the shadows of all 18 segments, and you also can see the outline of what's inside of the instrument itself, and we can see how well that primary mirror in the telescope is aligned to the instrument. And that gives us some initial confidence that the alignment looks good, and that's a good starting point for doing the alignment of the telescope. We have now gotten some data looking through focus, and we've been able to see that we don't see any surprises in the shapes of the mirrors that we're looking at. So far so good, but we do have a long way to go.
Right. Oh, stop the video. Okay.
That's fantastic. I love how, like, in some of those reflections or some of those images, you can actually see the shape of the mirror in there as well.
I'm curious how they got that selfie. Where's the light coming from? Because it's shaded. It's behind the sunshade. It's supposed to be in the dark. Was that just starlight on it?
I think so, yeah.
I'm not sure.
They went to a lot of trouble.
Have a look.
They went to a lot of trouble to make that sunshade, to keep it cool. So it should be in the dark. Yeah.
Well, they're taking that selfie in infrared light. So it is, it would be with whatever light is hitting the telescope from outside.
Okay. Sorry, I'm just going to go back. I'm just going to do do my share again. Oh, okay, there we go. And I wanted to go to there. Just a minute. Hold on. Let's just do this again. Oh my gosh. Oh, okay.
Just click outside the video.
Outside the video. There we go.
There you go.
Okay. Sorry. Thank you. So if people are have not been kind of just checking in, I wanted to just show you as well that you can go to a really cool website that is called Where is Web, and it should come up. It did before, but it's not. There we go. The James Webb Space Telescope. So this is just a website that you can constantly kind of keep track of what is happening about the. I think this isn't actually filling in some of the. Oh,
And you.
oh, sorry, it's not.
You're
It
only
wasn't
sharing
working.
your presentation screen, not the web page.
Oh dear. Okay. Do you know what? I'm going to move on for this. I'm
Okay.
sorry. This is I'm going to stop the share here. Hold on. Okay. So if you go to the Where is Web website, you can find how many days it's been, how many days before it goes, exactly how cold the different parts of it are. You can find out exactly where in the progression of what's happening with the telescope all the time, exactly what's happening and what day it is. So it's really very cool that you can kind of watch that. Anyway, I just wanted to kind of bring you up to date. Chris Gaynor, if you're still on, is there anything more that we need to know that's happened with the telescope that we could share? Putting you on the spot a little bit.
Hello. Well, I missed. I just stepped away.
Okay.
The first few things you said, but of course the big news this week is that they've turned on the fine guidance sensor
Yes.
from which is part of our Canadian contribution, and it works fine. And I think you might have shown those
Yes.
18 stars
Yes.
all lined up.
Yeah.
So that's the big news now. It seems they're coming up with stuff all the time. I thought a couple of weeks ago it'd be a snooze for a while, but there's always something coming up.
But there's always something new coming up. Okay, thank you. And we'll just keep going. We'll just keep going with that. One of the other things that we kind of talking about what's going up and what's coming down is that there was, and maybe Chris, you can help me out with this as well, is they were talking this week a little bit about the decommissioning of the Hubble Space Telescope. And online, I found a site that was talking about they're going to let it come down and they're going to crash it into the ocean in about 2032. Is that about right, Chris? Is that what they're looking at? Like
Yes,
they're not going to crash it with another telescope or anything, or with another satellite or anything. They're just going to let it come down and crash into the ocean. Is that correct?
No, that's right. There's sort of a lot of estimates of when it's going to come down, and actually, in theory, the NASA is obligated to send a little spacecraft up to it to dock and then make a controlled reentry, because Hubble is as large as a school bus.
Right.
Now, chances are, if it was just left to random chance, it wouldn't hit anybody. But some of us will remember the big fuss about Skylab back in 1979, when that's more or less what happened. Not quite, but close to it. So Hubble doesn't have thrusters. But as far as I know, that spacecraft that's supposed to dock with it has not been devised. In the last servicing mission, which is nearly 13 years ago now, they did attach a little docking fixture.
Yeah.
So we'll see what happens, and of course we could get into a situation where Hubble could just die one day. There's a number of possibilities, so it'll be interesting to see how it shakes out. But anyway, the goal was, they wanted to get at least a couple of years of joint operations with JWST, and we're getting pretty damn close to at least the start of that goal. So we'll see what happens.
Well, if it does stay up until the 2030s, it will, have been 40 years in operation. And
That's right.
you know, it would be amazing. Okay, so the only other thing that I wanted to talk a little bit about was, again, just talking about things that are you know, possibly not going up or not going down at kind of the right at the place, is the Artemis mission that the Canadian Space Agency has been talking a little bit about, and that is that is working with NASA in order to have the unmanned Artemis 1 that was going to go up. And in fact, if you look through some of the sites, it was to go up before, like in you know, kind of 2021, and then they were going to have it completely done by 2022, and now it has been delayed, and they haven't even got it to the launch site yet that is going up. And so it's kind of, it almost sounds a little bit like the JWST is you know, that they're not going to put it up until it's completely right. So that's the first mission. That's Artemis 1, that's going to be sent out as an unmanned mission that will go in a very large orbit, kind of all around to the moon and then back again. And then the next one, Artemis 2, is going to be a crewed mission, and the Canadian astronauts are to be included in that one. It is not going to land on the moon. It is one that is just going to be sent up and do the orbiting of the like quite a long way around the orbiting of the moon to test all out the systems and see what's everything is going to be on. But that's kind of interesting that those are, I believe, 2 out of the 4 people on that will be Canadian astronauts. And then Artemis 3, now that was supposed to go up, I believe, originally in about 2023, 2024, and I think that's also been delayed. But what's interesting is that the Artemis 3, which is the one where they're actually going to go and have 4 astronauts on the moon, of which NASA has said that one of them will be a woman that will land on the moon, and the other one will be a person who is Black, who is going to be on the moon. And that they are promising that will happen, and that they are going to be putting that one up. Well, they talk about the delays for Artemis 1 and the delays for Artemis 2. In fact, some of the sites were saying that because China and Russia seem to actually be kind of doing quite a lot of things right now, that in fact that NASA may get into that whole thing of, well, we want to be first again on the moon and not have the other people on the moon, and that we might actually pull that one a little bit forward. Now, in the same way, the what was called Gateway, which was a smaller space station that was going to be done so that it could orbit the moon, and the Canadarm3 is going to be part of that Gateway mission, is now kind of not necessarily going to be something that has to happen before the astronauts go to the moon. And I think, again, we're kind of almost back into a little bit of a space race for who will be the next set of people on the moon. So it's an interesting dynamic between, you know, what's delayed because of technology and what's and what politically what might actually happen. So just some new things that are happening out in space. You could just keep going on forever with everything that's happening out there. It's just absolutely amazing. Yeah.
Mhm.
Aaron,
Very
did
cool,
you have
yeah.
anything else?
Yeah, I have one more thing, but
Yeah.
I'm glad we don't have to wait until Artemis 11 to get back onto the moon.
Oh,
Not like the Apollo missions.
No. Elon
Um,
Musk is going to get there first.
We'll see. Sorry, that's my cat scratching something in the background. Yeah, so okay. The last story we have for tonight is about the rogue piece of rocket that is going to hit the moon shortly. And I'm a big fan of this story. So basically, there is an upper stage of a rocket that is in an orbit that is going to uncontrolled orbit that is going to take it smashing into the far side of the moon on March 4th. Now, this was originally identified as the upper stage of a Falcon 9 rocket that launched the Deep Space Climate Observatory in 2015. But some students actually from University of Arizona managed to correctly identify it as a Chinese rocket from the Chang'e 5-T1 mission. Basically, the original identification had been made based on some orbital parameters as well as the brightness and comparing that to the estimated brightness of the Falcon 9 rocket. However, the Falcon 9 rocket was in a much too low orbit. And while the orbits can change through like fuel leakage from unburnt fuel in these rockets, it would have taken an unusual amount of fuel to get it up to an orbit high enough to hit the moon. Even though it was going in, the observatory was going into geostationary orbit. So this other rocket was identified a little bit later using the same monitoring network that called Project Pluto that tracks near-Earth objects. But these students actually managed to catch the error before Project Pluto. They took spectra of the reflected light coming off of that rocket and found that it didn't match the spectra of a Falcon 9 rocket. We can get that by looking at other ones that are orbiting, and it comes from reflections off the metals and the paints that are used in the construction of the rocket. And they found that it didn't match the Falcon 9, and it much, much more closely matched the spectrum seen from other Chinese rockets and the paints used on them. So they were able to identify this and publish that before the Project Pluto caught the error and made their correction. Either way, though, this is a big chunk of metal that's going to hit the moon. Unfortunately, you won't be able to see it from home because it's hitting the far side, but I'm really, really hoping that one of the lunar reconnaissance orbiters is in a good spot to see it, but we'll see. So keep your eyes open on March 4th, and we'll see if we get a picture of a new crater on the moon.
Is the Chinese rocket a little red shifted?
Depends which way it's going. All
That's
right.
bad, Chris. Okay.
All right. So that's the what's going up, what's coming down for this month. And with that, I'm going to turn things over to our astrophotography group, our computer-assisted astronomy folks, David, Lee, and I think we have Brock on today. So David, are you ready?
Yeah, I am. Well, good evening, everybody. So I think I see Brock on the online. Brock, do you have some stuff for us tonight?
I do. I have sort of my since New Year's. I have collected a few shots. I thought I could share those.
All right. So Brock will have some images for you tonight, and I'm actually going to do some non-photography stuff. I'm going to tell you a little bit about a photo op, actually, a lunar occultation that's happening on the early morning of February 22nd. And Dave, are you there? I can see you there. Hey, Dave. So Dave's going to tell us something about cataclysmic stuff, maybe some remnants of cataclysmic stuff.
Yeah.
So supernova remnants. So that's pretty exciting stuff. I think I'd like to maybe start with Brock and then maybe have Dave, and I'll finish off with the occultation.
Okay.
So anytime you're ready, Brock.
Okay, I will share a screen here. Whoops. Showing my background. That's actually what I wanted to show. Can you guys see the horse head?
Yeah, I do. So just for some background, Brock, you're
Yes.
using a CMOS camera, and are you predominantly using a dual band filter to emphasize certain wavelengths?
Yeah, these are actually all taken with a color camera, a CMOS-based cooled astrophotography camera. And I'm using a dual band filter, which basically just passes the hydrogen alpha and the oxygen bands. And it makes it a lot easier to deal with things like full moons, which it seems whenever it happens to be clear in the winter, it also happens to be a full moon. and if it's not a full moon, and it's not going to be clear for some reason. So
Yeah, and it helps with light pollution as well, right?
I live close to some nurseries or some greenhouses that have about 1 trillion watts of high pressure sodiums, I think. So it's a little bit of skylight. So I have to deal with that. But yeah, this was actually one of the first ones. We'd had like 2 months of awful weather, and we finally in early January had a clear night, and I managed to capture the Horsehead Nebula, and I was pretty happy with it. It's not a lot of data, so it's the details a little faint. There's, I hope to get back on that target before it moves out of the way and we're into galaxies only.
Yeah, so just for our viewers, often what is done when we commonly call it capturing data, but often photos that you'll see are accumulation of quite a number of subframes. And Brock, how many frames do you have here?
I should have had that in front of me. It's probably somewhere in the neighborhood, I think 50.
Okay, so normally what we would do is we would add frames, and it doesn't have to be exactly at the same time when you photograph the originals. Sometimes it could even be a year later, but
Yes.
These things don't move around too much. So we have an opportunity to just keep adding frames to it and getting more and more detail.
This one turns out it was 70. So I looked it up.
There you go.
I should get
Yeah,
this stuff
very
all
nice.
lined up. Had a busy day. Didn't really prep. But I also, I really wanted to capture the Pleiades, and I missed it last year at Seven Sisters, which is a beautiful group of stars. And basically, it's what the Subaru logo is based upon as well. If anyone out there owns a Subaru. But it's a gorgeous target. The reflection of these stars and the various gases around them and dust clouds.
This is quite an interesting depiction, Brock, because normally when I see this, the backgrounds are quite black, so not as much exposure as this. And in fact, I'm quite impressed by the red star that's nearby. I've never noticed that before.
Yeah, it's it's quite striking how there's very young bluish stars, and there's a few much more reddish orange colored stars nearby, where at least I don't know if they're nearby, but they're in the same field of view. It's always hard to tell if they're actually truly nearby.
And you certainly have a lot of kind of like dust in the area too that we don't always see in photographs.
Yeah. It worked out well. It was this one actually wasn't with the filter. This was actually just a bare sensor, because of course it's not a target that's made up mostly of hydrogen emissions or anything like that. It's just white light reflecting off the clouds of gas nearby and clouds of dust as well. So it turned out quite well, and I think this one was actually 41 separate images that made it up in the end.
Presumably the yellow red stars are field stars, though.
They're not in the same area. Is that what you're saying, Ben?
They're just line of sight, because
Yes,
if they were that bright, they wouldn't. If they were the same brightness of as the blue stars, they'd be red giants.
Right. Right.
And they're a bit fainter, but if they were regular main sequence stars, they'd be very much fainter. So they're almost certainly, just field. But what you would do is measure how fast these things were traveling, and find whether they were actually associated, because all the stars in the Pleiades will be traveling at the same speed in the same direction. And the field stars wouldn't necessarily be. And that's how you usually tell these things apart.
I have to build my spectrometer.
Yeah, do some radio velocities.
Yeah, just for the people in the audience that are not camera people, this is a very easy object to find with binoculars. So
yeah,
a binary object for sure.
Or even with your bare eyes, it's one of the real standouts on a dark night. It almost to some extent looks like a teeny tiny mini Big Dipper. I think there's this group of these stars here, I think, are some of the brightest, and almost creates a little, at least to my bare eyes, well, at least with my glasses on, It
Yeah,
looks
I do.
kind of
I
like
do
that.
remember in the days, the distant days of public outreach, showing people the Pleiades through my small refractor, and that's often what people would say. Says, "Oh, is that the Little Dipper?" And I said,
Yeah.
"No."
No, it's next one is my second. Actually, I did 2 nights where I was looking at Orion, and I got the first night with some data, and then I went back and got a whole pile of extra shots of it, and was able to actually get I think a grand total of 124 images to integrate on this one, which gave me a lot more ability to bring out some of the subtle clouds in the darker areas around it.
I'll tell you, it's amazing, Brock, how much cloud is illuminated by those stars.
Yeah.
We did some recent test shots at the VCO, and I just had never noticed how much backlit cloud there was in the area, especially around the trapezium, in that bright area in the center there.
Yeah, the center there, there's a little cluster of, well, they're not little, but if I zoom in, you can actually see there's, I think, 4 distinct stars that are essentially the brightest right in the center that are illuminating most of the nebula.
Yeah. You can, one of the nice things about this sensor that you have, Brock, is that because it's such a, how many megapixels is it? I can't remember now.
I don't remember off the top of my head. It's
a big number.
6,000 something by 4,000 something pixels.
Okay, so maybe in the 40 range.
40, yeah, in that range, probably.
In the 40 range. So for the non-camera people, again, that really gives us a lot of zoomability, what I call zoomability.
Yes.
You can actually kind of look in there like with smaller or lower resolution cameras, you can zoom in and you just see kind of muck, right? Just fuzz. Yeah. But with this larger sensor, you definitely have this ability to just kind of zoom in. And I think that's been the big thing for me, even with this big sensor we're working on at the VCO. It's like 60 megapixels. That zoomability really gives you a new kind of insight into looking at the images.
It does. Another big benefit of these newer sensors is the dynamic range. This is a 16-bit sensor, so it is able to both get the data for these faint wispy clouds that are barely, hardly any brightness at all, but yet it actually has enough dynamic range to still not have the intersection of this blown completely out. Most sensors, you have to choose one or the other. You either expose the dim regions and blow out the core with just being way too bright and essentially, railing your sensor on that end, or you choose the other. You just can't normally get them both. I was amazed that this would actually do the entire dynamic range of the thing without having to do some sort of a multi-exposure composite or something, which I actually did last year. I did with a much less capable camera. I did exposures at different, I did 30 seconds and 120 seconds and 180, and I combined them because I had to try to get the most out of it. But this is just the same setting for everything, much better.
Yeah, it is for sure.
In the same region, not too far from Orion is the Rosette Nebula, and I've done a couple shots of it since January, and I combined all the data, and I did a bit of a unique interpretation of this one, in that I thought I wanted to really emphasize the fact that it kind of looks like a tunnel, and rather than trying to show the faint stuff around the outside, I really darkened it to really kind of draw the eye to the center. And another thing that was done with this is there's some artificial intelligence based software that essentially can detect stars and remove them from an image. And so I gave a crack at that just to kind of add some additional dramatic look to this, because I thought it was quite a neat way to show this object. And
yeah,
this again,
actually, in a very similar way, Brock, this one looks backlit as well. It looks like there's lights in the tunnel pointing back at us through the cloud formation.
Yeah, this is quite a beautiful target. It's
can you zoom us in a little bit? Let's have a look in the
For sure.
opening there. Oh yeah, you see, Yeah, that's wonderful.
Yeah.
Wow. It reminds me of the picture of the inside of my eye when I go to my optometrist.
Yes. Everyone says it looks like an eye. So, but yeah, I thought it's a beautiful target, and it's again, this was done with that dual band filter, and a lot of this image was taken with a huge moon. Like, it's amazing that even with the moon, I was able to get some good shots.
Yeah, that's actually one of the things that is saving amateur astrophotography is these special filters, because
Yes.
there's so much light encroachment now that
Mhm.
it is very difficult to capture good data, and this makes it possible.
Yeah. And then the next shot is a bit of a copycat. Someone I know did a nice shot of this that I realized last year, back in the summer, I was looking at different things I wanted to capture, and I saw pictures of the Crab Nebula, and I thought, oh, I want to get that, but I realized there's no hope in the summer. It's nowhere to be seen. So, and once I was aware that it was visible, I had to get it. So I just have a short period of time on this one. I think I don't know how many exposures I managed to get in, but
This is one of the famous Messiers, isn't it?
yeah. Well, this is
one that was just
Messier #1, so that must say something.
Yeah, yeah, and this was I think Aaron, correct me if I'm wrong, but this was the one that the Chinese discovered that was actually visible during the day.
Yeah, this was actually 1054. Chinese astronomers had recorded the supernova. So this is actually, I won't get into it too much because I think Dave's going to speak a little bit.
Yeah, it's going to be a good segue.
Dave did a beautiful shot of this, but it's a supernova remnant, the leftovers from a supernova that's actually not all that old. So, but I was lucky enough. This was almost a full moon, and again, back to those great sensors and the amazing filters.
That's amazing detail, Brock. I mean, typically when I see M1, it's quite fuzzy, and it doesn't have the detail in the core like you have.
I guess I was lucky with that night. It was and of course it was high in the sky. So some of the other targets I've gone after, I didn't show it tonight, but I did go after the Thor's helmet, but it's so low in the sky and the seeing was terrible. So the guiding was terrible. Everything was terrible. I'm going to need a lot more data before I show that one publicly.
Yeah. So again, for aspiring astrophotographers, you want to aim for capturing these targets at least above 30 degrees, I would imagine, maybe above 45 if you can, right? Just so that you're not looking through that swimming pool of atmosphere that's really at the edge near the horizon. And
one little picture at the end is not a great shot, but it's just kind of a preview of things to come. I did get a galaxy. So I was a lot of these targets, they're all kind of starting out the night almost directly overhead. So there's only a few hours before they actually fall down below the horizon. So then the telescope's it's 1 in the morning and there's nothing to look at anymore. So I set my telescope to go and find a nice little spiral galaxy after it had finished up on the Crab Nebula. And so I had this nice, because we're moving into the time of year, the way that the night sky works, of course, is as the season progresses, the Milky Way basically falls out of view, and we're looking, rather than looking through the plane of the galaxy, we're looking out into open space, and the visibility of galaxies basically becomes much, much better, and you can't see the Milky Way anymore. So the sort of close by targets like things people, the Horsehead and the Pleiades and, the California Nebula and all those things that are part of the Milky Way are not visible, and it's time to go look at galaxies. So over the next few months, anyone who's into looking at the night sky or taking pictures will be focusing mostly on galaxies. So it's kind of where we're headed.
Yeah, the galaxies can be quite challenging, Brock, because then not all of them are really large, like M31 and
yes,
and some of the larger ones. Some of them are quite small.
This is M99, so it's a very small. Well, it's a big galaxy, but it's in the field of view. It's very small. So this is actually cropped quite a bit. It was quite a bit smaller in the raw image, but I took it because I was looking for galaxies that had quite a bit of hydrogen emissions.
Oh, the red stars.
Yeah, just
Yeah.
red stars and also nebular,
Or the nebulosity, I guess.
regions that are hydrogen emission regions. Because I knew I had that filter in there, and a really white sort of, a lot of the galaxies just wouldn't have looked very good because the dual band filter is not what you really want to use on a galaxy. But so, anyways, that's the last shot.
Excellent. Yeah, so Brock was doing a little bit of foreshadowing here. We've got some supernova remnants coming up with Dave. So yeah, maybe if you can stop your sharing, Brock, we can get Dave on the line. Oh, take it away, Dave.
Hi. Just trying to get my screen up. Good evening, everyone. Maybe I'll try the slideshow here. Yeah, I wanted to, Brock had some just gorgeous images there, and rather than compete with them, I'd rather take the low road and show you how we take these kinds of pictures. And specifically, I wanted to talk about supernova remnant imaging. Because these really come to life with narrowband or other false color type pictures, and I just wanted to share how we take them and how we can make them so colorful. But before I go on to that, I just wanted to talk a little bit about what a supernova is. It's basically a very violent explosion that happens at the end of the life of a big star, or when two white dwarfs collide. And it's basically a runaway nuclear fusion reaction. And generally, stars are mainly burning hydrogen to make helium, fusing hydrogen to make helium. But what happens with the supernova is you're getting a lot of heavier elements as helium fuses with itself, or hydrogen, making heavier and heavier elements. And this all gives off energy, and when it takes up, it all of a sudden runs away on a star near the ends of its life. And that causes the star to blow off all of those elements that it's been making, the ones that exist in its outer shells, and the rest collapses into a small neutron star or even a black hole. So the star itself isn't the only thing that gets excited when this reaction takes place. The astronomers tend to as well. And when you hear a report of a supernova happening in a distant galaxy, everyone tries to focus their telescope on it and take a picture of it. To show you these explosions get so bright, what we have is a distant galaxy here in the lower left. Here is a picture of one in the Virgo cluster. And you can see right here is a supernova that's taking place just on the outer edge of that galaxy. And it's the only single star you can see in that entire galaxy. So they're just so burn so brightly, but they don't last long, sometimes a few days to a year before they're essentially gone, and they've become the neutron star, and you basically can't see it anymore. The remnant material, though, we can photograph because they emit light as they absorb gamma and X-rays, which we can't see from that leftover star. So the remnant material exists as an expanding cloud of dust, and a lot of different elements in it. So a lot of the elements in our periodic table are created during this explosion. Unfortunately, our human photon detector can only see 3 colors. So what this means is we can actually look at any sort of ternary system and make them colored and make very colorful images of these supernova remnants out of them. The one on the left is actually made up of 3 colors representing X-ray photons, infrared photons, and optical photons. So you can see the wonderful colors representing the different kinds of photons in this case coming from it. And I've just done an artist's rendition of what a typical supernova remnant looks like. This one is probably unrealistically spherical, but gives a good impression. So we in our backyard can't really, don't have X-ray capabilities or marginally infrared capabilities. So what we do is we use different kinds of photons in the visible spectrum to create our false color images. So the remnants are actually rich in many different elements, as I was saying before. In fact, most of the heavier elements that we see and we have on Earth and that we use to build things actually are the result of supernova explosions, because generally in a star you can only fuse up to iron at 26, and iron at 26 atomic number is a nice stable low energy atom. So elements less than iron at 26, here it is Fe, tend to fuse together and give off energy, and elements heavier than iron, when they come apart, they give off energy. And so everything smaller wants to point to iron, and everything heavier wants to point backwards towards iron. So I just wanted to get across that there's a lot of different elements in these supernova explosions. And the other thing I just want to briefly talk about is that each of these elements, and here's an example of 5 different atomic elements, each one has its fingerprint of colors or frequencies or wavelengths of light that it gives off. And this has to do with changing quantum numbers, quantum energies of the electrons as they move within that particular element. So what you see is a spectrum, and this is how, as astronomers, we can tell what a certain star is made out of, based on the fingerprint associated with each of its constituent elements. What we can do in taking photographs is we can use filters to hone in on one of the spectral lines of each of these elements. And then we can use that to photograph specific elements that are being blown off in the supernova remnant, right? These filters will also pick up on the broad spectrum. They'll pick up a bit of light of that. So you still see stars that are emitting a broad spectrum, but you'll also pick up the highlights of the individual elements. And here's an example of a filter that you might use. And we tend to use 3 because we can only see 3 colors. The 3 spectra I show here, they're designed to capture the exact wavelength or frequency of spectra emitted by oxygen, hydrogen, which you've heard a lot about, and sulfur. So by using specific filters, and 3 to capture these elements, we can get different pictures. We can get a picture of each of these elements alone and where they are in the supernova remnant. These 3 are the most common that we use. And all we have to decide when we're taking a picture is who gets to be red, who gets to be green, and who gets to be blue. Now you see 2 of these spectrums are red. Hydrogen alpha is red, and sulfur is actually a bit deeper red, and oxygen happens to be a greeny blue. But we get to decide based on our artistic license. So essentially these filters are generally contained in a filter wheel to which we attach a mono camera. So it only takes black and white, and it only takes in the photons that happen to pass through the filter. Here it is at the end of a larger telescope, a reflecting telescope, and and the same cameras on the end of a refractor. Now, going back a little bit, I just want to talk about the specific supernova remnant that I'll show you some pictures of. And Brock showed one. Here it is in the upper left. This one is just taken using visible light. Now you see a lot of pictures taken with just visible light of nebulosity, such as a supernova remnant, generally are red. And that red is what is given off by hydrogen. And in this particular one, you see red and you see white, which is basically the material given off by all the other elements and hydrogen. So this is a fine picture, but it's not particularly colorful. So one thing about this supernova remnant, it's called M1, as you've heard, and it was the first in Messier's list of things that weren't comets. He was actually in the 1700s looking for a comet, and he settled on this object for a little while, and I guess he got frustrated and said, damn it, I'm going to make a list of things that aren't comets so that people looking for comets won't look at them. Became a famous list. The actual supernova, the star that exploded, was noticed by the Chinese in 1054, and it was called a guest star. And I wondered if that's what doomed King Harold, because 12 years later, he lost a battle. This one was bright for about 1 year. So this guest only hung around by 1 year. And what we see today is what's left over, the remnant. It's still expanding today. And we can see, based on its expansion rate and the size of it and how far away it is, that it's about 900 years old. And that's why we believe that it's the same supernova noticed by the Chinese astronomers. It's actually about 13 by 11 light years across and expanding very fast at 1,800 kilometers per second. It's about 6,300 light years away. So when I say it's 900 years old, it's really 7,200 years old. But that's just the time frame. It's lit up by the X-rays and gamma rays. Some interesting facts. It's the star itself now has a mass of about 1.4 suns. But it's only 30 kilometers across, so in diameter. So it's very, very dense. And when it was a star, it was about 9 to 11 times the size of the sun. So that's a lot of that material exists today in the supernova itself. It's now, the brightness of the whole remnant is about 1,000 suns, but the total luminosity, including the light that we can't see, is the equivalent of 75,000 suns. So it's a very bright object. So I took 3 pictures with the 3 filters and decided to assign hydrogen alpha to red. The sulfur element I assigned to green, and the oxygen element assigned to blue, rather arbitrarily, but I knew this was going to give me a good colorful image. But you can see through the different filters, the character of the remnant is very, very different. So what we do is we stack them with their assigned colors, and we get the glorious jeweled color that shows a lot of the detail inside the nebula by taking these narrowband shots. And you can see, you don't just see red, green, and blue. In fact, you don't see green. What you see is the mixture of the elements coming through, but you can tell what elements are most concentrated and where. That's not the limit of the processing you have. Here I did a bit of hard processing to see what detail I could see within the nebula, and you can see it's actually made out of very fine elements of color, as if the cloud is being existing in strings. Of course, the star that exists at the center you can't see, but if you did have an X-ray telescope, you would see it as extremely bright.
Dave, there seems to be, if you go back to that slide there, to M1, there seems to be like a cloud around it. Is that a processing artifact, or is that a real thing?
So there is a cloud around it, but unfortunately M1, I'm going to blame the weather on this one and the moon. When I took these images were taken over 3 nights. When I went to take the first set of images, it was a clear night. It looked like I was going to get a few clear nights in a row, so I picked this image. But unfortunately, M1 is right on the ecliptic, and along comes the moon, and I didn't get clear nights in a row. I had to wait. And by the time I had my second and third nights, the moon was very close. It was a half moon, but it sat almost on top of M1. So that, coupled with a little bit of haze in the air,
Which would have been lit up, right? Yeah, I see that.
So I'll go back to this and get some more shots, but I wanted to. I was dying for some color in my nebulosity, so that's
Dave,
there.
Before you move on, it's Ben here. I wanted to the pulsar in the Crab Nebula is one of the most fascinating objects in the sky. I wanted to quickly show you a short movie. If you
sure.
So in about 1969,
Can I stop sharing?
I'm not sharing quite yet, but I can share this one here. Want to quite show you this. In 1969, they discovered the pulsar was actually radiating in optical wavelengths, and there are about 2,500 pulsars known, and only about 6 have ever been seen in the optical. And the Crab Nebula one is the brightest one. And the Chandra X-ray Observatory in space took this little time-lapse picture of that. This is right in the core of the crab. And when you watch the movie, it looks like this.
Wow. Yeah, like waves.
Yeah, so you see, and just so you know, this pulsar is rotating 33 times a second.
Yeah.
Sorry, 30. Yeah, it's a 33 millisecond pulsar. It's not the fastest known, but it's one of the fastest known. Oops, excuse me. I don't want to do that.
1600 RPM, so I can relate it to my car.
Yeah. So this, can you imagine? This thing is about the mass of. This thing is about the mass of the sun, more than the mass of the sun, 30 kilometers across, and rotating at 33 milliseconds speed. And further, the fastest pulsars known are around 5 or 6 milliseconds. So it's not even a record. It was in the early 80s, they discovered a pulsar going round at 6 milliseconds. But why that is a completely different story, which I won't talk about right now. But anyway, back to you.
Yeah, thanks, Ben.
Well, all that angular momentum has to go somewhere, right?
Yeah, well, that's right. So when a single star collapses, obviously it spins up like a skater pulling in their arms, and that's why pulsars rotate so fast. But all right, the reason why their pulsars spin even faster is because they can be spun up by having a disk around them, and matter falling into that can torque the star and make it go even faster.
So would you say that whatever a black hole is, it's got to be spinning like crazy.
Most likely, yes. So in relativity, there's there's a difference between the way individual stars have gravity and fast rotating stars have gravity. The gravitational field warps in a somewhat different way. But yeah, it's a fair bet. But the real thing is black holes have event horizons, and it's not completely clear how the stuff inside the event horizon is connected to the outside. There was a long time where that was an unsolved problem. But nevertheless, the accretion disk around a black hole, the material there is spinning very, very fast.
Thank you for that. These supernova remnants are just some of the coolest things out there, and they double as very gorgeous photographic subjects too. I just thought I'd show a couple more. This is of a different supernova remnant. This is part of the name escapes me.
Veil.
This is Pickering's Triangle, part of Cygnus Loop, which is a much older, much bigger supernova remnant. It's nowhere near as bright, but it's much larger, and it just the skyscapes that you get from photographing it in narrowband are just gorgeous. Here's one part of it. Here's another part called the Western Veil. They just and the other thing that fascinates me about them is the actual separation of the various elements. You can see that they're moving in the same direction. They're kind of getting pushed differently, but they seem to move at different speeds out from, or given off at different times or in different quantities during the supernova, because you see that they're actually in distinct places. Well, thanks.
Well, thanks, Dave.
Go too long.
No problem. Yeah, that's wonderful. I love cataclysmic stars, but you're right. So they don't really last that long. But actually, there's actually recurrent supernova as well. So they actually don't quite blow up. They just blow up a little bit, and then blow up a little bit, and on and on and on. But yeah, so thanks very much, and also that great explanation of the narrowband is wonderful. It complements the stuff that Brock's done. So now for something completely different, I'm going to tell you about, now can everybody see something that says lunar occultation?
Yes.
Oh, great. Okay, so basically on February 22nd, we're going to be able to see two stars, or actually it's really one bright star and then a dimmer star, approach the bright limb of the moon and then reappear on the dark side of the moon, darker limb of the moon. So this occurs in the south to southeast. Now I'm just going to give you an idea of what to expect. If you have an opportunity to check this out in the next couple of days, see if you can spot the star. This is quite a really easy thing to do without any kind of instrumentation. It's best with at least binoculars, though. You want to at least highlight the area where the star enters. So this is actually, as I say, this is in the south-southeast. It's occurring with stars that are actually in Libra. So this is what we call the scale. Now, these stars, Zubin al-Shamali and Zubin al-Ganubi, some of my favorite Arabic names for stars, were originally associated with the Scorpion Southern Claw because they thought it was at one time related to Scorpius, which is down here. What are we looking at? So we're looking at these two stars here. Now, the one that you're going to be watching, this one's moderately dim. This one is like a MAG 275 or 2.8. And then as it approaches the limb, this is the one to be looking for. So when does that happen? Well, for people that are in Victoria, this happens at 2:45. So this is not for the faint of heart. Either you're an insomniac or else you're willing to get up early, or you do what I do and I take a nap. So 2:45 is when the disappearance happens. And then you got to wait till about 3:53 when it reappears off the other side. Now, for those people that want to do this in the future, if this doesn't pan out, this is a good website here. This actually lists bright stars that are occulted by the moon. And by the way, these stars like Zuminel Canubi, for instance, they're falling along with Libra, falling along the ecliptic. So it's not uncommon for these stars to be eclipsed. So here you go. So I hope you take up the challenge. Certainly you can also image it as well. So for extra points, if you want to try imaging this and create a little movie, I encourage you to do so. Make sure you set up a little bit ahead of the times of these events. And like I say, always take a nap. So anyways, if you have any questions, you can get a hold of me here at david@victoria.rsc.ca, either how to find it or maybe how to image it. So thank you tonight for Dave and Brock, their wonderful astrophotography. So we're off to another good year for this, and hopefully the weather's going to get better.
Can I, before we go, one thing that ties together some of what obviously the presentation Dave did, but also the stuff about the pulsar at the center. Do you mind if I just quickly?
Yeah, go ahead, please.
There's a guy in Austria. Can you guys see this?
Oh, wow. Look. Oh, is it pulsing?
Well, it's a repeating image that's actually 10 years. A guy with a 0.5 meter telescope in Austria took pictures every year for 10 years. And you can actually see the expansion of the Crab Nebula.
Expanding and contracting.
Well, it's not, it's just repeating over and over again. But,
okay, sorry. Okay.
So but you can see the expansion, but you can also see, and I didn't really get what I was seeing until we saw that other thing about the pulsar. But if you look in the center, you can actually see the motion, circular motion of the plasma.
It's like the ripples, like throwing a pebble in a pond, right?
Yeah, and it's from that rotation.
There's quite a lot of material out on this that shows the dynamics of that disk rotation, and so you can imagine. One of the things that we do know, of course, is the pulsar is pointing towards us, because we wouldn't see it. It's a beam. What looks like the disk is rotating that way, but the beam of the pulsar, which we think is from its magnetic pull, would be pointing towards the Earth. So pretty cool, huh?
It's amazing that you can actually see it changing over time. And the same is actually true of the Veil Nebula, the one that Dave showed. Hubble has images that they've taken of the Veil Nebula over close to 30 years, and they've actually used the differences that they can see it expanding, and they've been able to calculate the velocity that it's expanding at. And pretty amazing. Everything looks so static when you take a picture, but it's not as static as it sometimes appears to be.
One other example of like expansion seen over a timescale like that is V838 Monocerotis, which is a light echo from a nova that happened in a big gas cloud. Great way to look at. But we are a little over time, so I'll maybe show that one next month. But I just want to say thank you to all of our computer-assisted astronomy folks. Excellent images as always. And thank you to everyone who's joined us this evening. Sorry about the technical difficulties on YouTube. But if you enjoyed the show tonight, please head back over there and subscribe to our channel so you get notified of our future live streams and star parties. Again, follow us at FriendsDAO on any of the social medias, and we look forward to seeing you next month. Clear skies, everyone. Have a good night.
Good night.
Bye. That was wonderful, Brock and Dave. Wow.
Oh, yeah, amazing.
Beautiful. Really, really excellent. Yeah.
I thought we might run over time. But
Yeah. Yeah.
Just a little.
That's okay.
all right.
No, Dave, that was a really good explanation. And I got a bit of information that I didn't know. This for Dave Payne, a bit of information that I didn't know that just went, oh, right, of course. It's one of those things that just like you hear about all of it, but it all just kind of just fit together.
I think Dave's off the air.
Oh, is that okay? Well, you can tell him that.
I'll tell him that. Yeah,
Yeah,
for
that
sure.
would be good.